Hello, and welcome back. Today I will be continuing with building out the physics engine by implementing the collision phases discussed in the previous video. So to recap, we'll use a BVH to accelerate collision queries amongst colliders in the simulation, and these colliders are a type erased wrapper over geometry, and these geometries can be either a sphere, a capsule, hull, and triangle mesh. The three phases we'll be looking at are first the broad phase, which we will be detecting collider nodes in the BVHs that potentially overlap. The second we will be looking at is the mid phase, which is trying to detect which triangles the collider potentially overlaps. And then finally here in the narrow phase, we will confirm collisions against the underlying geometries of the colliders using a series of overlap tests to return collision information for the contact resolver to use. Before we get into it, I want to apologize for having to delay yet another implementation video. While working on this one, I came across a problem with the internal collision checks that had to be solved, and I've also been trying to balance my time with something to come later, and that's a new convex decomposition algorithm. There's more to come on that, but it's been a very fun and time-consuming process. It's also been very challenging. However, let's jump into the task for today, and that is our collision phases. All right, so let's start like last time by building out a little skeleton for the code. This time we'll be creating the structures that will be used to keep track of the collision objects throughout the phases. So the first structure will be a collision pair, and the collision pair is simply a mapping back to the potential or later confirmed collision objects, and it also stores the collection of potential triangles that should be detected during the mid phase and collided against during the narrow phase. And so this looks a little like this. We have our first collider, second collider, and then a vector of triangles. I'm gonna have to add that one. Bear with me here. Sorry about that. Anyways, the vector will store the triangles, or the pointers to the triangles that come from the triangle mesh. The next struct is the contact manifold, and the contact manifold will kind of remain a black box for the time being, but in the deep dive in the narrow phase, I'll be filling this out and discussing it a bit more. However, for now, just know that it simply exists, and this is what's created during the narrow phase. And then the final struct is one I call frame collisions, and as the name suggests, it's a vector of collisions that happen during the simulation frame. And it has a set for non-mesh collisions and a set for mesh collisions. This could be combined, but in the mid phase, you have to ask the question eventually, is this a mesh collision or is it not? And I just like to ask that question in the broad phase before I get to the mid phase, so I can just go over this single container. And then you'll also have your set of contact manifolds. Again, these are just a black box for now, but we will go over them later. There's some more additions as well, but as those comes up, I'll add those as they come up, as it's just more natural that way for those. Okay, so let's begin with the broad phase. And we'll break the broad phase into three parts: internal dynamic collisions, dynamic versus static collisions, and then dynamic versus terrain collisions. I've touched on this before, so I'm not going to go over that too much. However, here in the BVH file, we need to add two functions. One to check for internal collisions, and this will take in a list of BVH nodes. It'll take in, I don't need to take a reference to that. I'll take in two node indices, and these will be indices into that node vector there. And then we also pass in the frame collisions. And this will be used to record the potential collisions. And then for, sorry about that. For external, it's kind of the same thing, or same signature. But instead, we take in a second vector of nodes, and we'll call this one the primary BVH nodes, and we'll call this one the primary BVH index. I'll call this one the secondary BVH nodes, and then secondary BVH index. And let's go ahead and add the functions. Have to add the contact manifold. All right, and now we can begin to fill these out. All right, so we'll start by looking at the external first because we'll actually use this when we do the internal collisions. The first thing I like to do is just makes it a little easier. Go ahead and grab the references. And then after this, we'll need to check if the AABBs of the nodes are overlapping. And I will actually have to show this real quick. I forgot in the updates, these are the overlapping functions. So these will be used during the narrow phase to check the underlying geometries. This is used during the mid phase to gather that set of potential triangles. And then this is used here during the broad phase to check for overlap between node bounds. If there's not a overlap between these two nodes, we know that none of the children of these two nodes overlap, so we can return. However, if there was overlap, we need to check to make sure that either of these, or that both of these are leaves. And if they're both leaves, then we know that we have a potential collision. So now the goal is to figure out what type of potential collision we have. So we want to see if we have a mesh contact. And what we're going to do is we're going to check the collider of node 0, or of the nodes. We're going to check their colliders. We're going to check the collision volume and then the underlying geometry. And we just simply say if one of these are underlying a mesh, then this mesh contact will be true. And it's just a Boolean. All right, and depending on what this mesh contact is, we'll determine which vector we grab. Do a little ternary check. If it is a mesh contact, we want the frame collisions mesh collision. And if it's not, we want frame collisions dot non-mesh collision. And then we'll add in the collision pair to the proper vector. Again, the reason why we store the collider is because the collider has all of the physics information that we need. If one of the nodes was not a leaf, we descend deeper into the tree and check for overlap of the inner structure. We ultimately continue this process until we reach both leaf nodes or rule out collisions altogether. For descension, we'll first check if node 1 is a leaf, and if so, we know that node 0 is not a leaf, and we can descend further into the primary nodes. And the way we can do that is by calling this function again. We'll send the primary nodes, we'll send the secondary nodes, and now for the primary index, we're going to use the primary node children. And then we'll simply do it again for child 2. Likewise, if node 1 is not a leaf, this doesn't mean that node 0 is also a leaf, but what it does mean is that node 1 has children we can descend into. And so that's really it for the external collisions. Now we're going to look at the internal collisions, and it's actually just a series of mini external collision checks. So first, we, just like here, we'll grab our nodes, and it's, like I said, a series of mini external checks. So the first thing we want to do is we'll call the check external. We'll give it nodes, nodes, and then we give it node 0 index, node 1 index, and then the frame collisions. And then this process just continues iteratively until the leaf nodes are reached. And so we say if not node 0.isLeaf, we'll check internal collisions. And we'll give it the nodes, and we'll do it with the first child now. So this is going to split apart the children into their own mini external sets. It also help if I could spell. And then we do the same thing with node 1. So this is kind of gross, I won't lie. If you understand how this works, you're kind of defeating the purpose of a BVH. We're supposed to accelerate our collision queries, and this just kind of does a BFS all the way down until you reach all your leaf nodes. When I was originally fixing this, I did remember a technology I actually displayed way back when on the channel called BVH blocks. And now the whole idea of the BVH block is that at some point it just becomes too expensive to traverse down the tree because you'll have so much overlap in the higher levels of volume. So if you split up your BVH your BVH tree into separate blocks, due to the fractal nature of it, I mean, as you can clearly tell from the internal and external reuse, if you can find a pattern somewhere in the fractal, it exists throughout the whole thing. So if you split the BVHs into smaller blocks and then check against the blocks, you can get better performance that way. In some case, I mean, everything needs to be tested, right? But in the BVH block test on this channel, for the performance it was going for, that was clearly a gain. So I'm leaning towards repurposing the spirit of that system to handle this internal check mess. But there's more to come for now. But this is the how the broad phase collision is performed. And now let's take a look at the optional mid phase. So before we do mid phase, I forgot to actually implement these tests. So the first thing, do dynamic, make sure that it's not just a root. We'll grab the root itself. We'll grab the root, and then we'll do our check internal collisions. Give it the nodes, give it child 1, child 2, and then the frame collisions. Oh, that's right, we need to add those to the contact detector. I can't tell you how many times I'll come across a bug or an error where I know for a fact the code works, or it should work, and I just didn't include the code. right, so now for dynamic versus static, we'll make sure that the dynamic colliders have a node count, have some nodes to collide against, as well as the static. So this one, we'll just simply do the check external collisions, and we'll give it the dynamic nodes. We'll give it the static nodes, and then we can give it the dynamic root and the static root, as well as the prime collisions. And then it's exactly the same thing, really, for terrain collisions as well. So you just add in terrain colliders. I've explained before why terrain colliders get their own set of BBHs, but that will be your broad phase. Now we can step into the mid phase. Okay, so the mid phase is called optional because it's possible you either A, don't need it, or B, fail to detect any triangle mesh collisions in the broad phase. The entire purpose of this phase is to find the set of triangles which potentially contact the underlying geometry. Now, in the theory video, I said that this could be expressed as the statement: we want the set of potential triangles that exist in the triangle mesh such that for each triangle in this set, an intersection between the chunk that contains the triangles in the mesh and the node collider exists. It's quite a mouthful, but it's expressive enough to get the idea across what we're doing. This has actually been slightly changed to say, instead of looking for an intersection with the triangle chunk and the node collider, we say an intersection between the triangle and the mesh's chunk and the node collider exists. The purpose of this change was for the convex decomposition I briefly mentioned. The algorithm will decompose a small set of triangles on the fly and create a partial hull. Again, there's more to come on this, but that's the reason for this change. The decomposition aside, this approach would also help in just creating a reduced set of potential contacts. Okay, so all mesh colliders themselves are two parts. They're a collection of triangles, and then they are an octree that accelerates these triangles. And the octree nodes themselves simply store back pointers to the triangles in the original mesh. And it should be said that the octree used for mesh colliders is specifically designed for them, so I won't be going over it in too much detail, but you can probably derive how they work from just looking at the decorations here. And it's just a normal octree, there's nothing too special going on. Okay, so getting back to the collision process, the first thing to do is write the mid-phase loop before I forget, like last time. So to do this, we will be going over all of the collision pairs that we registered as a potential mesh collision, and that'll be stored in our frame collisions. Okay, so it's building. And now we're going to want to grab our colliders. And the next thing we're going to want to do is make sure that they were ordered correctly. So we want to make sure that A, collision volume, is not a mesh, and if it is, we'll go ahead and swap the non-mesh collider with the mesh collider, and this way our pointers are in order. And this kind of goes back to, oh goodness, this whole making sure that the lower geometry comes first, and everything is lower than mesh. After we do that, we want to go ahead and descend into the mesh collider. And we're going to store all potential, not spell that word, potential triangle collisions. So we'll want to grab our mesh. Get it from the collider like that. And then we'll need to do something to get back our physics ID so we can access the AABB that bounds this collider. And once we have that, we can go ahead and get its position. And if you remember in the actual manifest code, this is a little different because I don't use a map, but it's just to express the point. You want some mapping back to your colliders and their physics IDs so you can reference the appropriate objects throughout the various parts of your engine. And finally, we'll go ahead and grab the actual AABB from the BBH that this physics ID maps to. Node index. And bounds. And then we'll go ahead and write out actually the next thing we'll need to do, which is create some skeletons, but we're going to create two functions that will handle the collisions. One to just begin the collision, which is this one, and then one to recursively check the children. All right, sorry about that. I had to fix some typos. All right, so hopping back into the awk tree, we're going to need two skeletons, or two functions rather. And we're going to write out the skeletons now. The first will be to check the awk tree, and then the second will be to check the awk tree node. To check the awk trees, we're going to start, we'll begin by calling check collision with awk tree. And we're going to send it the AABB, the awk tree, and then the container to store potentially contacting triangles. And then that function will build up a list that dispatches into this function to check the children nodes. After that, because we use indexing, we want to pass in that node index. Pass in the triangle mesh, and then a queue. And it's this queue that we'll use to build up basically which children to search next. These are So let's go ahead and start with this one first. It's already defined. Interesting. Start this function. And we're going to create a queue that takes in potential node indices. And then we're also going to want, actually, we don't need that. So we just want to push onto it the root index. And then now, while there is something to work on, we're going to grab the index, go ahead and remove it, and then we will pass that index into the other function to check for collisions. Also, I apologize for the delay. Trying to talk and type is not my forte. Alright. Oh, the queue. Fix the queue. Alright, so now let's move on to the next function. So this function is actually fairly simple. We're simply going to go ahead and grab the node, and then we're going to want to check if this node is a leaf or not. If it is a leaf, we're going to go ahead and check each of the children. And what we're looking for is if the child is active. So if the child index is a null index, or if it's not overlapping the node collider with this this particular node's bounds, sorry. Yeah. We go ahead and return. Go ahead and break out, or go to the next one. And if we do detect overlap, we push it back, or just push this child index for further checking. Or if we are working with a leaf node, we're going to go ahead and copy all of the triangles, out of the octree into the triangle mesh. Triangle pointer. And this is just going to check if the AABB is overlapping the triangle. What are you not happy about? Probably this. Okay. There we go. Okay, so stumbled our way through that, but that is those are the checks for grabbing the triangles out of the octree and sending or copying them for further checking in the narrow phase. And then, simply this just repeats until we run out of indices to check. So that leaves us now with just the narrow phase. The narrow phase is quite a challenge. In this phase, we're no longer working with the simple AABBs, but rather the underlying geometries reported to be potentially colliding in the previous phases. Same as before, we'll begin by writing our skeletons. And for this phase, we're only going to have one check, or one function we need to write out. And we'll call it check underlying geometries for collision. And it will take in a collision pair, would be the potential collision. And it'll also take in sorry about that. We'll take in a vector of contact manifolds, and these will be progressively built out as we check each of the collision pairs. And then here in the narrow phase, we can make a little lambda, and in this function we will simply pass in a collision pair, and then call that function on it. We'll pass in the potential collision, and then the frame collisions contact manifold vector. And then we'll just do a loop over each element, and the non-mesh collisions, and then we'll do the same for the mesh collisions. So one thing that needs to be added before we begin to write out this function here is we need to put in a way to return the underlying type of the enum class. So this will just simply be able to return back the sphere as a 1 or a capsule as a 2. And we will use that because this function is broken up into 2 parts. The first part will be creating a collision code, and then the second part will be using that collision code to calculate, or to rather call, the corresponding overlap function. So this will be a new int 32, underline A, and then we'll give it A's underline type, and then we'll do the same thing here all over the place. And then we'll put it together into the collision type or collision code. Both are the same thing. And we want to make sure that B is the last, or is the upper nibble. So we'll shift B by 4. And then we will make sure that you are checked to enforce that the high nibble is always a greater or equal shape. We'll go ahead and swap A and B, so the pointers will be pointing to the correct geometries, and the collision type, we will just simply recalculate it in the reverse order. Alright, and then now we can move on to the overlap functions. So if we take a look at the overlap functions, we see that they're booleans. And the reason for that is we are going to use another lambda, and this function will be called, or record collision, and it will take in the result of the overlap test. And what it's going to do is, if we're not overlapping, it's just simply going to return. But if it is overlapping, we're going to go through each of the newly created contact manifolds. And one thing I forgot is, because the overlap functions actually allocate new manifolds, before we go in and do the test, we're going to record the number of current contact manifolds. Then what we'll do is, from that point to the new end, we will go ahead and take the contact manifold and we're going to copy over the collision data for it. And I don't believe, yes. So part of the contact manifold, its internals, I guess I can just go ahead and fill it out now. It's going to get a collision pair, and it's also going to have a vector of contact points, which is another structure that was meant to just be a black box, but it will be just for now. And then we'll also have a vector normal, and then something called a constraint type. For now, these are more to come. Anyways, getting back to it, the reason why we have the collision pair is because we're going to store the A and B, and the reason why we don't store this collision pair here is because we may have potentially had to do this well. So now we can go into the second part. Give me a second. Oh. It's always one of these boys that will get you. All right, and now we can go and simply do our switch on the collision type. And I'm actually just gonna copy this over because you'll get the ID here in a second. But what we're doing is we are checking the collision type to see what the underlying geometries are. So let me clean this up first, and I will be back. All right, sorry about that. Then when we're done here, I'll actually go into the collision detector in Manifest to show the actual layout. I do apologize for having to bounce things all over the place to get the dependencies to work. But nonetheless, we simply switch on the collision type, and then we just examine the bits. So a sphere, it's going to be 1 and 1, and so we know that we're going to want to take our A and our B and turn them into spheres and call their corresponding overlap function here. And then we simply just go down the list and do that for all of these. And then they'll go in, and there's going to be a part 2 to this where I actually go over each overlap test. Actually, it'll probably be 2, one for non-mesh collisions and then one for mesh collisions. But nonetheless, depending on the result of that, we either just return or we go ahead and copy over the corresponding pointers so that we have the physics information for the collision resolution phase. But with this, that's really the end of it, and I will hop into the actual code base now and show the layout. Okay, and as promised, here is the actual code layout in Manifest. As you can see, all of the collision detection is actually, all the overlap functions are handled in the static intersection file, and that's implemented by the contact detector, which has the phases and that underlying geometry check. The static intersection includes the contact manifolds, which include the colliders and define all of the structs needed for the collision detection and resolution process. Here in the collider, we have basically what was built out in the project, and then just references to each of the individual colliders, and the colliders themselves just store their definition and then the encapsulate function for putting an AABB around them. But that is it. That is the entire collision detection pipeline as implemented in Manifest's physics engine. I hope you enjoyed. If there's anything you feel I left out or need better explained, please let me know and I will be happy to help. With that, I will see you in the next one.